Right, we're very happy to start this morning session with Daniel Areán from IUC Madrid, who will tell us about non-Hermitian holography beyond the horizon.
Yeah, I hope. Okay, first, thanks a lot to Les and Frank for organizing the program, for having me here. It's been a very nice week. I like this kind of programs with relaxed, like not so many talks, but time to discuss. Although I've been a bit busy finishing the grading and that, but I enjoy the talks. And thanks also all of the speakers I've seen this week. I hope you do more programs like this. It's very nice. Okay, so this morning I'm going to talk about this idea. Hopefully it's also related a bit to the title. So we have open systems in the title of the systems, and in principle, non-Hermitian physics can be used to describe open systems. So we'll see. First, let me say I will talk about ongoing work. I mean, the main idea of the talk is to discuss ongoing work with David García Pariña, PhD student at Madrid, and Juan Pedraza. It's called. He has a permanent position there. So at IFT, you know him, or some of you know him. And but of course I have to introduce the subject, so I will discuss also mostly, maybe more than half of the talk will be about previous works with also David, but also with Carl Steiner in Madrid and Ignacio Salazar in La Plata. So this is a bit the outline of what we'll be talking about. I will introduce the idea of non-Hermitian PT-symmetric quantum mechanics, which is a very lively field with many applications. You feel like optics and cold atoms, quantum simulations, many things I don't know. But you can go, for instance, to this nice review and see a lot of theory and applications of the field. Then I will discuss how to implement a very minimalistic model of how to implement PT-symmetric theories, how to build holography-friendly PT-symmetric theories, quantum field theories. And then I will present and discuss the features of a holographic model that includes this feature. Okay. So let's start with please. Also, let me say that please ask questions. This should be a mostly very easy idea. So if I'm not doing a good job of being clear, please tell me. Because as you see, at least in the beginning, we will start with very easy things like this two-level Hamiltonian, okay, that we can picture like two boxes. This Hamiltonian, of course, has two eigenstates of the same energy. And this is, of course, very easy, very symmetric, and of course, Hermitian quantum mechanical model. Here are the eigenstates. Of course, they are unitary, probability is conserved, everything is okay. We have two real energy states. This is the spectrum. Okay. It's already diagonal, so you don't have anything to do. But you can very easily make this thing non-Hermitian by opening it and adding a loss and gain rate that we call gamma. So you deform your Hamiltonian to something like this, which in principle you would say is very sick. Your eigenstates become imaginaries. Of course, unitarity is lost. And which is what you would expect if you open the system and you leave influx and outflux of energy. Okay. But you can fix this if you also add hopping. Okay, you add an off-diagonal part to your Hamiltonian matrix that allows you to hop from what was one eigenstate to another. Then your spectrum, you diagonalize this, and your spectrum is this. And now if gamma over G square the absolute value of gamma over G is smaller than 1, these are still real numbers. Okay, and this is okay, you can also picture like this. I realized yesterday that here in this picture, I'm taking this capital E to be 0, but okay, the idea is otherwise you would write capital E plus this other E. But okay, this is a picture of this very easy, very silly thing. And you see already some features that are typical of PT-symmetric systems in this plot. Okay, that you have these two eigenvalues as a value, and then you study them as a value of some coupling that introduces, in principle, a non-Hermitian deformation. And you see that if, of course, when this gamma over G is larger than 1, these eigenvalues become imaginary, and actually they meet at 1, with this is called exceptional point. And then beyond there, you have a complex spectra. Okay, but before your spectra is real, and if this is just a manifestation of something that can be formalized, and it's the fact that PT-symmetric systems have real spectra. Okay, and this is what I'm summing up here. You have a system like this, and you have three phases of theory. You have the PT-symmetric phase when this is real. You have the PT-broken phase where the eigenvalues become complex. Your eigenstates, what's happening is that eigenstates break PT. I haven't introduced PT yet. I will now. And then they meet at the exceptional point. Okay. So yeah, for instance, I haven't done it, but this Hamiltonian that is not Hermitian is PT symmetric. Okay, you can implement here PT like this P reflection and T just conjugation, complex conjugation, and this is PT symmetric. But of course, the eigen, okay, I didn't show you here the eigenstates, the eigenvectors, they are a bit ugly, but when this becomes complex, also the eigenstates break PT. Okay, this has been going on mostly since the 90s when Bender started looking at this type of systems. But it's been a bit more formalized by Mostafa Sadeh in the 2000s when he showed that this is showing something more generic, that is, and if you have a PT-symmetric Hamiltonian, you can actually do something more, and you can map it back to Hermitian Hamiltonian. There will always exist a map that is called Dyson map, that you can also view it as a metric in your field in your Hilbert space, a non-trivial metric that brings you to a Hermitian system. Okay, so the only requirements is that you have an antilinear symmetry. You call it PT, but what you require is this, that commutes with the Hamiltonian, shares the eigenvectors, because of course if the eigenvectors break this symmetry, this is what I will call a PT broken phase. Shares the eigenvectors and is antilinear, okay? So it's conjugation on the eigenstates. Then you can show that the systems that have this feature, there will exist a map to an Hermitian system. Okay, this is a similarity transformation. Something like this. You have your non-Hermitian Hamiltonian, and you can transform it to a Hamiltonian small h that will have a real spectrum. Will be Hermitian. So this small h, you can move it from the K to the Brad. If you do it with a large h, instead, what you have is that it is Hermitian or self-adjoint with respect to a metric that you can construct in terms of the map. So it's back and forth. Okay, and this has had many applications, mostly in quantum mechanics, in some simulations. So these are systems that the idea is something like I show in the two-level system, that you have some gain and loss that is compensated, at least when you're in the PT-symmetric phase. So the idea has been simulated, for instance, in lasers with gains and losses, optical systems, also called atoms, and quantum simulations. That I know. Less is known about realization of this in quantum field theories, but there's also been quite some activity. And then a natural question is, well, at least for us, maybe it's not for everyone, but one can ask himself what is the phenomenology of this non-Hermitian in strongly coupled systems. Okay, so a tool for that is to use holography. But first we have to come up with easy models like of non-Hermitian theories that we can describe in holography. Okay. So since I'm changing a little bit, let me know if you have questions about this very easy introduction. not, I will move on to a model that is very amenable to holography about how to introduce to have a non-Hermitian PT-symmetric theory that we can describe hopefully with holography. Okay, so a very easy way to do this is to start with a CFT. Start with a CFT because, as most of you know, CFTs are some CFTs are easy to describe in terms of gravity, their gravity duals through holography in some regime, of course, strongly coupled and large N, all the limitations that holography usually. But okay, we start with a CFT, and a very easy way to do a non-Hermitian deformation is through a complex operator. Okay, so we add a complex operator O, and of course it's Hermitian conjugate O bar, and their sources I will call them S bar and S. Okay, it's easy to see that this theory is going to be PT symmetric if I take the sources to be real. I will show it. But of course, you can probably change frame in that sense. Nothing physical will change. And to make this deformation non-Hermitian, for instance, we can take both sources to be real, so PT is still respected. But if I take them to be different, of course, the system is non-Hermitian. Okay. And this is what I'm summing up here. We can implement PT like this, some reflecting one coordinate, and then we take the operator to be a scalar under PT, and we choose the sources to transform as functions. Okay. This way, this axiom will be non-Hermitian. Okay, of course, assuming that the CFT, non-Hermitian, PT symmetric, assuming that the CFT is PT symmetric. If we take the sources to be real, PT symmetry is respected, but if we take the sources to be real and different, S different from S bar, this is of course not equal to its conjugate, and we are in a non-Hermitian setting, but PT symmetry, as long as the states respect PT symmetry. Another nice way of this implementation is that the Dyson map, so the map that brings me back to a Hermitian description, is almost for free. It's already built in, and it's nothing else that the U1 symmetry that the complex operator brings, but complexified. So if I take my U1 symmetry, under which, of course, the operator transforms as a phase, as a U1 phase, but now I make my phase imaginary, then this becomes a similarity transformation. And for instance, let me start with, this is the usual thing we do typically in holography when we want to switch on a complex deformation by a deformation of a scalar complex operator. We can choose the phase, so we typically take the sources to be real. So I start with something like this. With my real source, I call it M. This is Hermitian. Now, if I apply the U1 rotation, nothing will change. And this is my U1 freedom that I have. But if I make this phase complex, the phase imaginary, then instead of a phase rotation, is this kind of exponential map. And then my axiom becomes something like this. Okay, now O and O bar rotate with S and S to the -1, but now this is of course not just a phase. So this is not Hermitian anymore. This is a subtlety that it won't matter here, but if my phase is space dependent, then I will also switch on a current of this U1 conserved symmetry. Okay, this won't appear in the rest of the talk because I will take my deformation to be homogeneous in space. Okay. So I'm summing up this here and also like picking a kind of nice way of parameterizing my non-Hermitian deformation. Okay, so here I started with some source that I call M. It's a constant source, real. I apply that map, and then I get to some two non-Hermitian sources. But instead of starting with M, I start with something that I call 1 minus eta squared, square root, such that when I apply my U1 map, I can check that the U1 map will act like this, and I get to tune to this non-Hermitian scenario, which is what I want you to take Okay, so now I have two sources, S and S bar, that are sources of a complex operator, O and O bar and O, and they are real and they are not equal by an amount that I call eta. Okay, so if eta were 0, I would be in the Hermitian initial scenario, S equal M equal S bar. But if eta is some number between 0 and 1, this is not equal to each other, and I have switched on an Hermitian deformation. Okay, this map works up to eta equals 1. I mean, I could have chosen a different, in terms of my original variable of the U1 deformation as an angle that became imaginary. It would be eta equal 1 would correspond to the limit beta to infinity or to minus infinity. But parameterized like this is very nice to make plots and everything. Nothing physical. And it's also good. It's also easy to visualize where the exceptional point is, which is at eta equal 1. Okay. This is also telling me how I can compare things in the phase where PT symmetry is respected, and I know how the map works. Which is if I have some observables in my non-Hermitian theory at eta equals some value 0.3, I can map them to a Hermitian theory with a source, okay, slightly with Hermitian sources, but it's so 1 minus, but the number I get from this map. Okay. As long as this map works and everything's fine, I will be in what is called a pseudo-Hermitian theory, because I know how to map everything back to a Hermitian theory. In this case, which I know the map. It's not always easy to know the Dyson map, okay? Especially in quantum field theories. But here it's almost for free. I just picked a theory where actually I reverse engineered it, okay? I know how to how to start with a Hermitian theory and do this complexified U1 rotation and arrive to an Hermitian. So another recap before moving to holography. Let's see if you have questions. Is that after discussing a bit the concept of non-Hermitian quantum mechanics, I try to convince you that it's very easy to have a non-Hermitian deformation of a CFT through a complex operator, okay? Complex scalar operator. I also try to show and convince you that I have the Dyson map that brings me back and forth between the Hermitian and the non-Hermitian theories. And just let me state here again that I parameterize the non-hermiticity in terms of this number that I call eta. And the range of parameters for this eta is between 0 and 1. And in that range, okay, the range of parameters for this eta doesn't have to be between 0 and 1, but when it's between 0 and 1, I have a Dyson map that brings me back to a Hermitian. Okay. If you're interested in what happens where I do this non-homogeneous, you can go and to our paper where we studied this and did things like, for instance, a non-Hermitian junction, kind of junction where you have you put together Hermitian and non-Hermitian theories, and you have nice features that can also probably be simulated. And maybe have been. Not of course for strongly coupled system theories. Okay, so now that I have this framework of how to do an easy non-Hermitian quantum field theory, let's try to implement this in the setting of holography, where it's easy to describe the setup that I just told you about. So most of you know about holography, and also there's been some lightning introductions this week, but a very brief one with the bare ingredients we need for this setup is this. Okay, we know the Gates gravity correspondence tell us that in order to describe, we can describe a conformal field theory, a particular conformal field theory in the Larsen limit, in the strongly coupled limit, and through its gravity dual. So its gravity dual is going to be some some space in one dimension, space-time in one dimension more. So in this case, I will talk about CFTs that live in 2+1 space, 2+1 dimensions. So the geometric dual will be a four space-time dimensional space-time, a four-dimensional space-time that is asymptotic to ADS. So ADS, remember, is the space-time with constant negative curvature. And the gauge gravity correspondence tell us that let's say the UV of this conformal field theory or the Lagrangian lives or is encoded in the boundary of this space-time that is asymptotic to ADS. Okay, and then sources of operators, for instance, we have the holography. CFT is dual to space-time asymptotic to ADS. And now, if we want to, for instance, include deformation by scalar operator, how do we do that? A scalar operator, a complex scalar operator, is going to be dual to a field living in the to a field, a scalar field, complex scalar field living in this space. And Beffs and sources of this operator are going to be encoded in the boundary, in the asymptotic behavior of these fields towards this towards the boundary of the space. Okay, ADS has a boundary. The boundary, of course, has one dimension less, and this boundary is conformal to Minkowski. So there you can think that this is where this field theory action lives. Okay. So with this framework, it's easy to implement the idea that I told you about before, which is considering a CFT and switching on an Non-Hermitian deformation. Okay. This is the concrete action that we will take to construct this dual, okay, to this idea. This is a model that is being used for many applications, like for instance, describing strongly coupled superfluids. And what is this model? We have here like GR, so Einstein-Hilbert term with a negative with a cosmological constant. The cosmological constant is that which allows me to have vacuum solutions that are exactly ADS spacetime. Then I'm dealing with a complex operator, so I didn't emphasize this, but complex operator has a global U1 symmetry. And through the gauge gravity duality, global symmetries are encoded in terms of gauge symmetries in the bulk. When I say the bulk, I mean the spacetime with one dimension more than my field theory. So I need also a Maxwell term for those to encode as those symmetries. And then I have my complex operator, which I call phi, and it's going to be charged under this U1 symmetry. Okay, this U1 symmetry, you can view it as the gauge symmetry is implemented in this global U1 symmetry that I was telling you about, that I used to rotate my sources and make the theory non-Hermitian in this case. So a bit of technicalities, well, not so much. The mass of this scalar operator is going to be, of this scalar field, is going to determine the mass dimension or the energy dimension of the dual operator in the CFT. In the CFT, you can classify your operators in terms of how they behave under conformal transformations. And this is, their dimension is set in terms of the dimension of the mass of the dual field, okay? So in this case, in what I will be telling you about, I will be taking m squared equal -2. This is something you can do because even if it looks like a negative mass, this spacetime where it lives is negatively curved, so it's still taken free and it's stable, and that's not a problem. Okay, I mentioned here that I'm keeping the chemical potential equal to 0. You can ask, I haven't talked about chemical potentials. I could have switched on a chemical potential through this gauge field, but I won't either, so we can forget that further. There's also this quartic term that is also interesting because it will allow me to have some kind of enhanced symmetry in the ground state of my theory. In particular, this allows to have solutions for the people who know that are RG flows from ADS to ADS. That means that in the IR of my theory, so I have a theory that is asymptotically conformal in the UV. That's why my space is asymptotic to ADS. Then I switch on a deformation through this scalar. In principle, you break conformality, you don't know what will happen in the IR, but thanks to the quartic term, you can recover again conformal symmetry in the IR. Okay. This is not needed for being able to do this non-Hermitian holography, but it will help in some cases. So how do I implement my non-Hermitian deformation in terms of this eta parameter? So it's very easy. If you go to what is called the holographic dictionary and tells me that the sources of the operator dual to this scalar are encoded in the asymptotic behavior of this field phi towards the boundary. Okay, the boundary. Did I write the metric? Okay, this is the metric. This is the asymptotic form of the metric. Of course, this is GR coupled to matter. You have to solve everything together. And your spacetime, if you didn't have matter, it would be something like this, which is the metric of ADS, or at least a wedge of it. And as I said, I wanted the solution to be asymptotic to ADS, so my spacetime has to look like that in the limit C to 0, which is where the boundary is. And there is where I identify the sources dual to the sources of my dual operator. Okay, so what I have to do to implement the deformation I was telling you about is solve for the system of coupled matter and geometry, imposing that the scalar field behaves like this towards C equal to 0. So that its derivative, the derivative of phi goes like 1 minus eta times m, and the derivative of phi bar goes like 1 plus eta times. Okay. This is in principle a conformal theory, so m, let's say, is the units of my deformation, and I will measure things in terms of it. So I will have a phase diagram. This is like a teaser of what I will be discussing. I will now study my system as a function of my non-Hermitian deformation, and I will also consider thermal state. So I will consider adding temperature. As I said, since the theory was conformal in the beginning, I will have to measure things in terms of, for instance, of the mass of my, let's say, the energy of my deformation. If I had a chemical potential, I could have chosen a different normalization. Since I show this diagram here, I can discuss it a bit, but this is what I will be talking about in the rest. I apologize for the drawing, since we've been talking about AI this week. I tried to giving this to the AI, this was like a year ago. Tried to giving this to the AI and asking it to do it fancier. It was complete disaster. And probably wasted a lot of CO2. Maybe you have to pay for the pro models. I got even something worse that I will show you later. Okay. So now we have the model, we have to solve, didn't say it, but normally solving this, the equations, solving this, the Einstein equations coupled to Maxwell field and scalar fields. Normally you don't find, these are, of course, differential equations coupled. In principle, at least these are just codimension one, so they only depend on one variable, which is this radial variable. This, I didn't say this, but my dual spacetime has one dimension more that I'm calling C. And this dimension, you can think of it as dual to energy or to the parameterizing your RG flow of your dual theory. So equations will depend on this variable, and normally you have to solve them numerically, especially when you add temperature, which you do through putting a horizon, so a black hole in your geometry. I will say this in a while, because first I will talk about the zero temperature solutions. Okay, So you go ahead and solve your model with these boundary conditions for the scalar field, and you find solutions that I'm picturing here. And the solutions, the geometry that you build are spacetimes that are ADS4 and ADS4 on the boundary, and asymptote to ADS4 towards the interior of this spacetime. Okay. They are real solutions as long as you keep eta between 0 and 1, which is as it should, because you know that while eta is between 0 and 1, you have a way to map these solutions, or I will tell you that you have it, but you should believe that you have it because of how I constructed the whole story. So you can map these solutions to our Hermitian solution to the case where I just take a real source. And this is actually what is happening here. So for instance, I'm plotting here one of the metric functions. This is the this is some rewriting of what is called the work function. Okay, doesn't matter much. It's just to illustrate that I have real geometries. The boundary lives here, and this is the deep infrared. In this case, the space exists up to C to infinity. And the fact that this goes to a constant tells me that it's asymptotically ADS on this side and asymptotically ADS on this other side. And this is called a domain wall because my metric interpolates between two ADS. And by moving the non-Hermitian deformation, the only thing I'm doing is kind of mapping one domain wall into another. It's like I'm pushing the domain wall to the IR. And this I can understand in terms of the map, of the Dyson map, because I know that the solutions I was showing you correspond to this set of sources, S equal 1 minus eta, S bar equals 1 plus eta. But I can already see in the equations that I have a scaling symmetry that allows me to map those to a Hermitian solution where the sources are equal, real, and equal to 1 minus eta star, minus eta square m. Okay, so you see here that the domain wall seems to be moving towards the IR. This is very large eta, so towards the end of where the Dyson map works. And what is happening is that the domain wall is moving towards the IR. Okay, the metric looks like ADS, like the UV ADS4 for a long periods of energy, let's say, and only in the deep IR moves to another ADS. And this is as it should, because as you increase eta closer to 1, you are like killing your source. If I didn't have any source, my solution will be just constant. Okay, so I'm moving the domain wall towards the IR. This is just okay, like a nice check and that everything works as it should and the Dyson map is reproduced, but maybe it's nothing new. And another check is what happens when I get to the exceptional point with equal to 1 and I go beyond. So it happens also what you expected, that is that you don't find real solutions anymore, and you find instead complex metrics, okay? And you find two complex conjugate solutions, which I'm plotting here. This is, for instance, the free energy. I think it's the free energy or the energy density, it doesn't matter much. You will see more or less the same features. So up to eta equals to 1, you find just the free energy of your solution. That of course depends on eta, because you can think of, like, as I said, that as moving the source of a Hermitian theory. But at equals to 1, and what happens at eta equals to 1 is that your scalar decouples from the equation, and you have an empty ADS. Of course, you don't have any energy, it's just empty ADS. Boring. This will be the exceptional point in the holographic system. And if you go beyond, you find complex solutions, and you find two of them that are complex conjugate to each other. So this is reminiscent of what happens in the exceptional points in the, for instance, in the quantum mechanical model I showed you before, where we had these two lines meeting and then becoming complex. Okay, so this is also as expected. What is less expected is what happens if you add 10. Okay, so now let's consider the same system in presence of temperature. How do you do this in holography? Instead of just an empty ADS spacetime as I showed you here, or empty plus some matter that is going to describe this deformation, now you add a horizon in your back. So you put a black hole there. It's been shown and discussed first and checked in many ways that this is dual. The temperature of this black hole would be, adding this black hole would bring your theory to a thermal state, okay? With temperature, a thermal ensemble, with temperature equal to the temperature of the horizon. So if you do that, and you also look for solutions, now the surprise is that you can find solutions outside of the regime of validity of the Dyson map, and they are still real solutions. And PT is not broken. As long as the BEFs are real and metric is real, then you can check easily that PT symmetry is respected. Of course, it's not here where you have two complex conjugate solutions, everything. So here, you would really call it non-Hermitian and also non-PT symmetric. But here, you add temperature, and you see that you can keep going beyond eta equals to 1 and still find real solutions. Okay, and actually, you will find two branches of solutions. But the range of the plot is not so good to show both. I will show you in the next. So this is the first surprise that you can go, and it's also not surprising, as I will tell you in a while, because you could also have seen that in the very easy quantum mechanical model. Okay, let's stay with this. This was the, what am I plotting here? This is just, I will be plotting from now on several times. I will be plotting, for instance, the BEFs of the operator dual to my non-Hermitian deformation. I will plot in this product of BEF times BEF of O bar properly normalized, because this product is invariant under this Dyson similarity map. Okay. So, but we don't know, fixate on all these details. What matters is that, at least from this plot, is that I can go, you see, at the exceptional point, this goes to 0, because I can think that at the exceptional point, the scalar decouples from my system. And beyond, I still find real solutions, okay? Here also the space-time will be real and everything seems okay. Although, as I will discuss next, beyond here, my general relativity solution, my system, my geometry breaks the null energy condition, okay? You can just think of that as the fact that when you go beyond eta equals 1, the sign of the kinetic term of the scalar dual to this operator changes, okay? And it's very easy to show that for eta equals to 1, you are breaking the null energy condition in your solution near the boundary, okay? And this will have consequences.
Sorry, Daniel.
Yeah.
So you said that in this case, well, when eta is greater than 1, the geometry is real?
Yeah. At finite temperature. If I'm at 0 temperature, this happens, and you only find complex solutions.
But the thing that you were plotting, it should be always greater than, should we always be positive, right?
No, it can be negative.
It's the complex conjugate of something times itself.
Well, but not anymore, because now...
Okay.
Yeah, that's a good point, but yeah.
Because of the choice of sources, expectation value of O bar is not the bar, the expectation value of O.
Yeah, another interesting thing to plot instead is O minus O bar, which is what you would call like the non-Hermitian part of when you take it to be real. And you will also see that it becomes, that I don't remember, becomes non-zero from there. But yeah, you're both right. Okay, so I find these real solutions beyond the exceptional point. And actually, the features are richer. So, okay, here this is like the continuation of this plot to show what happens when you keep going, because you can keep going. So here I'm already plotting only the, let's say, non-pseudo-Hermitian part of the system, so for eta larger than 1. These are the two, the color code is the same, so this is the blue there, and this is like, these are real, correspond to PT symmetric real solutions. But this exists only up to a critical value of the deformation. And from then on, you find also complex metrics. Here, for instance, I'm plotting just the real part. There will be an imaginary part also from here on, only from here on, okay? And you actually will have positive and negative imaginary part. And so you will have two complex conjugate solutions from then on. And then the metric is also complex, and maybe it's worth thinking of those metrics, but we haven't. I will say a few things if I have time. And here the interesting things is that now you have this other branch here that keeps going, but it looks like it will diverge, it doesn't. And for instance, here I'm plotting the free energy of these two branches, okay? So you get exotic things. Because, okay, this is the pseudo-Hermitian part up to here. So let's say that here everything you more or less understand in terms of Hermitian physics. Now there are these two branches. Here I'm plotting the free energy, which is of course real. From here on, if I take the complex metrics, it's not real.
The color coding is not the same as on the previous
Maybe now it's not, no, yeah, sorry. The green, yeah, because now the coding means the solution of my numerics.
The yellow and the green.
Yeah.
The blue and the yellow.
Yeah, sorry about that. Yeah, and also this blue is completely different. Okay, but it's easy enough that we can understand it. So you see that there are two branches here of real solutions that here were, well, more or less also where the green and blue start is a bit blurry, but sorry, the blue and the yellow. These are two branches of real solutions that here correspond to here up to here. I'm not plotting the complex here, so here everything's real. But what I wanted to plot here is the free energy of this branch that keeps going. It will keep. If I plotted it, all of it, then you wouldn't see these features because it keeps going. Well, it goes up to 60, so it's not that much. I could have plotted better. I wanted to convince you that the free energy of this is not divergent when it comes back to the exceptional point. Okay.
Real
It's
energy.
It's real. Yeah. It's real, and actually it dominates over this one because you see it has less free energy.
I mean, in the eta greater than 1, like eta greater than 2.
I know. If I keep going, no, for there it becomes complex. If I go beyond here and take my complex metrics, my complex metrics, my complex geometries, yeah, the free energy is also complex. And temperature. Yeah, I don't know. Well, if you trust your definition. Well, I mean, it's not completely, it's still asymptotical LDS and you're still defining your sources to be real and what you want, but then the metric becomes complex in the interior. And since we were talking about whether Witten was a physicist or not, it's for the recording we should say that he is. He also studied these complex metrics and discussed when they are acceptable as when it's acceptable criteria for defining quantum field theories with complex metrics. Okay, but I know next to nothing about that. But yeah, if you keep going through here and study those solutions, they have complex free energies, well, complex energies. But this they don't. And what I wanted to show here is that this other branch, which I will be saying things about it, that has finite free energy and seems to be asymptotic to some finite value. As you here, the numbers are eta minus 1. So 0 here will be the 1 here. And I'm just studying the asymptotics of this green line when I reach 1. Because this green branch doesn't exist beyond back in the Hermitian, in the pseudo-Hermitian theory. So this is purely some solution that exists purely beyond the realm of the Dyson map. Okay. This other one is smoothly connected to your pseudo-Hermitian phase, but this other one is not, hence there. And actually, if you would think about phase transition, it would be strange because it has less free energy. So you would come from here, the free energy will connect smoothly to this other branch, but there will have a branch appears with much less free energy. Some people call this zeroth order, but
as you lower the temperature, the green line disappears, right?
Yeah, okay. As you lower the temperature to 0, this all collapses and these two branches disappear. Yeah, so if you lower the temperature, you can think of this as a bulge that emerges from 1 to 2. As you lower the temperature, this moves back here and the complex solutions start at 1, which is what I showed you here.
These are Lorentzian or Euclidean geometry?
Lorentzian. Okay, but what you do...
Are you going to explain to us why at finite temperature you can still find real solutions?
Yeah, this is
So you said that at 0 temperature, when eta is greater than 1, you only find complex geometries.
Okay.
Are you going to explain why this is no longer the case at finite temperature?
Why is the case that I can find also real solutions?
Yes.
Well, I don't have like a very...
You would have expected for this choice of eta, everything to be non-Hermitian. Yet you turn on the temperature,
well, I mean,
and it turns out that the range of Hermitianity,
No, it's non-Hermitian, it's PT symmetric. What is surprising is that it's PT. I mean,
So
this is also non-Hermitian here, but I know how to map it back to Hermitian. But in principle, when eta is different from 0, it's always non-Hermitian.
why is finite temperature extending the range of PT symmetric?
Okay, I don't have a clear, deep explanation. Maybe it would be good to try to see if the same thing happens, like for instance, doing some loops or something in quantum field theory and see if you have something like thermal mass. That I don't know. That's what I said, it was surprising. What I know is that it's easy in a system like this. You can also see that if you just, so this is clearly non-Hermitian, but if you do something like a very trivial thermal ensemble and you study the PT symmetry of it, you see that it is PT invariant even in the regime where this is non-PT symmetric. So it's like the thermal trace restores PT symmetry. This I can see it in this very stupid model. In the holographic model, I don't know how to. I know how to read it, but I don't know how to do it in the dual field theory. As you know, I don't even know the details of the dual field theory, of the microscopical description. Here I know I can do this thermal trace, and I can see that it's PT invariant. But it's unstable, which is also what happens in our solutions. So these two new branches that appear that are still real, still PT symmetric, although they are in a regime where I don't know how to map it, where the Dyson map doesn't exist, happen to be unstable, okay, linearly unstable. Just not so surprising if I should think that I'm in a regime where gains and losses are not compensated anymore. And as I was saying, okay, maybe like you anticipated with your question. Can I say something about why this is, or if this were to be expected, that they have a regime outside of the pseudo-Hermitian phase where my states still respect PT symmetry as long as temperature is non-zero? And for instance, in this is my second AA generated image. So I asked about a thermal bath. Well, first I got it with people there. Okay, but the question is, can you find something similar in this two-level system? And the answer is yes. And you see that the thermal trace, you do a bit carefully how the PT works under this trace. I mean, here you only have two states, so it's very easy. And you see that PT is respected. So the trace is equal to the complex conjugate trace of the PT conjugated operator. Okay. But if you also study like linear stability of this, you also see that as soon as you are in the regime, in the non-pseudo-Hermitian regime, when this gamma over G is larger than 1, which is when at 0 temperature I will have complex eigenvalues, small perturbations will give rise to unstable. Okay. So I'm doing pretty. Well, okay, I told you the basics. I wanted to say something beyond the horizon. 5 minutes per second. So I don't say I'm fast with the recap. You can read it, and you can especially ask me if there is questions. But what is the idea now? To focus on these new solutions and see the structure of the black holes, of the interior of the black holes. Okay. And this is related to all this activity in the last, let's say, 6 or 5 years, which is about the structure of the singularity of black holes dual to conformal field theories or to strongly coupled field theories. And let's say it started in these papers in 2000 by Frank, Arnold, and 2 more people, so Frenkel et al., where they, implemented again this knowledge that there was already from the 70s, that we know that the Schwarzschild singularity is fine-tuned. Okay, I didn't emphasize it a lot, but the black holes I was implementing in my holographic dual to describe a thermal states were Schwarzschild black holes. Okay, ADS is Schwarzschild, so black holes that are in black hole spacetime that are asymptotical ADS. So the Schwarzschild singularity, of course, is a solution of a vacuum solution of the Einstein equation, and it's easy to see that if you add matter, this singularity is destabilized, and instead this matter will diverge, typically logarithmically. Well, yeah, will diverge logarithmically, and instead of the Schwarzschild singularity, you get what is called a Kastner cosmology or a Kastner universe, which you can parameterize like this. And since I'm doing very bad with time, let's try to, okay. I don't know how to give a quick flavor of this, but this is another reflection of what is called ultralocality of the Einstein equation. So you can think that the space correlations decouple where they are close to the singularity, and like each point evolves separately, and you have this kind of anisotropic singularity, near singularity metric characterized by these exponents. These are called Kastner exponents, and from the Einstein's equation, you can see that they have to obey certain constraints like this. So a metric that behaves like this near tau equals 0 is what is called a Kastner. And you can go and read about all this interesting, for instance, the Bickel conjecture that is saying more or less what I said, that Einstein's equations become ultralocal, and near the singularity, you will have this kind of metrics, this kind of geometries, and you will have chaotic oscillations between different values of these exponents. But what I want to tell in the 2-3 minutes, I'm almost done, so it's not so bad, is what happens for the interior of the black holes dual to these non-Hermitian systems. Okay? So as I said, people started, there are many works on looking at the interior of geometries dual to strongly coupled field theories. And for instance, in this first paper, they saw that if you have Schwarzschild and you just add a complex scalar, a scalar operator as I did, the Schwarzschild singularity disappears, and instead you get a Kastner, as you expected from. Okay, so what happens in our cases? Okay, very quickly in the pseudo-Hermitian phase, where I know I can map my theory to Hermitian one, everything works as it should, and I get exactly the same with the Kastner exponents properly mapped. Okay. So I call pseudo-Hermitian for eta smaller than 1, where I know how to map my geometries and everything back to a real Hermitian geometry, where the sources are real and equal to each other. Okay, so I can map also the Kastner exponents and everything. But what happens in these two new branches? What happens? So if I keep going from eta, I'm working at finite temperature, of course, otherwise I wouldn't have a horizon, or at least at a non-degenerate horizon. So what happens is that in this first branch, I still get a Kastner singularity, Kastner cosmology. If I keep going onto the complex geometry, I also get a Kastner singularity, but now things are complex, but they still obey the Kastner constraints. This, again, is an unexplored feature. And what instead we focus about is this new branch. And this new branch is a new singularity that is non-Kastner. This is not forbidden or anything, because as I said it in the beginning, the matter I am adding to generate these solutions is breaking the null energy condition. So the constraints you use to say that the structure of the singularity becomes Kastner just from the Einstein equations, you also need the matter to be, let's say, conventional matter that obeys the null energy condition. This doesn't, so new things can appear, and it's exactly what happened. For instance, here I'm plotting the Kastner exponents, so these features of the metric that tell me that the matrix is Kastner and they obey their constraints as a function of my non-Hermitian deformation. Up to 1, I know that everything has to work, but because I know how to map it to a Hermitian, to a completely normal scenario, to a scenario of the paper by Frenkel. But from 1 on, things are, bets are off. And what happens is that as I stay in the first branch of my two solutions, I still find Kastner solutions, but at some point, this Kastner structure dies. You can see that the would-be exponents diverge, and instead we find a new singularity. I hid a bit of technicality, a lot of technicalities here, like we have to continue coordinates. First, we thought that the space was ending, but it wasn't. And in the end, we found a new singularity that we can also solve analytically the Einstein's equations near the singularity, so to get convinced that this is not purely numerics. And for instance, here I'm plotting you the Ricci curvature. The singularity would be at c equal to 0. This is a different c coordinate, but the singularity would be here. This is the numerics. This is the prediction from this kind of singularity that I could try to convince you that it's a milder singularity than the Kastner one. And this is mostly the new thing about this, the interior of these new geometries. And now, and this is the very last thing, one can ask if this singularity can be imprinted on some field theory observables, and probably yes. And it will be, but it's okay, I'll let you, since I'm over time, you can ask me later. But you can probably see effects of this new singularity with respect to a Kastner singularity in things like two-sided correlators of heavy operators, which are dual to geodesics, going from one boundary to the other. So there should be some cases where this geodesic will explore the region near this singularity. So you will, in principle, be able to see the difference between the typical Kastner interior and this new non-Hermitian interior. Since I'm over time, I finish there. Then if you have questions about this last, I've been a bit fast in the discussion of the interiors, so we can discuss later. And this is my outlook. And thanks for your patience. It's been a bit over time. Questions?
So what's the imprint of the Kastner singularities in this geodesics?
Okay.
Because back then they were in Festuccia and Liu, they were not discussing Kastner, right?
We're not?
They were discussing the bouncing singularities, but I don't remember that they were referring to Kastner interiors.
Well, I don't know in that, but they were, for instance, in Frenkel and Harnoland, no? They consider this.
Yeah,
And they saw how
later, right?
Sorry? Yeah, that's later, sorry. Yeah, but being very quick, I also. Yeah, so in Festuccia probably not, but in this other 20,000 paper, they did, and what they saw is that the Kastner exponent, so okay, what is this? This is the, so if the geometry is Kastner, it has a small, and the Kastner exponent PT is smaller than 0, asymptotically, geodesics that are asymptotically null, so with very large energy in the limit where the energy of the correlator becomes infinite, the geodesics will approach the singularity, will become almost null. So they will be closer to here. So the length of the geodesic will get non-analyticities. This is what was discussed in this other paper. We'll get non-analytic features depending on the values of these exponents. Okay. So the very modest imprint that we are sure about for the moment is that in our case, well, you can parameterize it, for instance, as the length of the geodesic as a function of energy. It will diverge when the energy goes to, no, it will go to 0, sorry, when the energy goes towards infinity. But it will go to 0 slower than any Kastner cosmology. This is, for the moment, we haven't been, in the Kastner case, you can do that, read the non-analyticities analytically. Here, we haven't been able, but we can bound the integral and show that it has to go slower than any power. So this is the only imprint that we are sure about. Okay, thanks for the prep questions.
All right, let's thank Daniel again. Yeah.